Hello everyone. Um, so today we have back our weekly seminar, and today we have the pleasure to have Francisco Fernández-Álvarez, who is going to talk about gravitational radiation in GR with non-negative cosmological constants. So let me introduce Fran. So Fran Fernández-Álvarez carried out his thesis at the University of the Basque Country under the supervision of José Senovilla. He has a 2-year postdoctoral position at the university and is a visitor during the whole 2023 at Queen Mary University of London, hosted by Juan Valiente Cron. He works in mathematical relativity and in particular in topics dealing with conformal infinity and gravitational radiation. And without further ado, so the stage is all yours, Fran.
Thank you, Edgar. So thank you for inviting me. It's a pleasure to be here. So today I'm going to talk to you about gravitational radiation in full general relativity, and I will consider a cosmological constant which is non-vanishing. So I will consider a vanishing cosmological constant, which is the case that maybe some of you have in mind, and then I will talk about the case with a positive cosmological constant. So, okay, so now this is not working, right? Yeah, very close. Okay. So the talk has 6 parts. So first, I will give you an introduction, which it's not going to be technical, because I want you to have like the big picture of what we did. By the way, I'm so sorry. So this work is based on joint works with José Senovilla, who was my supervisor. Okay, so first, as I was saying, I will give you like some non-technical introduction to the topic of gravitational radiation in full general relativity. And then the talk becomes more technical, and I will introduce conformal infinity for those who are not familiar with it. And then I will review the case with a vanishing cosmological constant, and I'm going to spend quite a time explaining you this case, because otherwise I think it's one cannot understand what we did for the case of the positive cosmological constant. And then I will go with the case of a positive cosmological constant. So just to give you some brief history of the theoretical developments in gravitational radiation. In 1918, so we have this quadruple formula by Einstein, which was done, as you know, in the linearized theory. So at the beginning, the concept of gravitational waves was very fuzzy, and it wasn't clear whether they were real or not, or just some artifact of the choice of coordinates. And advances in full general relativity came in the 50s and 60s with the work of many people. So you might have heard about Bondi and Sachs course members, right? But I think that there are names there that sometimes are forgotten, that like Pirani and Bell, for instance. And with the work of all these people, so gravitational waves became a theoretical reality of the full theory of general relativity. And in the next decade, there is a really fundamental work by Gerock. It's really nice because what Gerock did was to put all the previous results in the nice covariant and gauge-invariant formulation, which is very geometric, and somehow our work has the same spirit as the work by Gerock in the 70s. Okay, and now just two observational facts. I'm not going to enter into detail because I'm not an expert, but I think we all agree that gravitational waves are a physical observational fact now, with the first direct detection in 2015. But there is another thing. If you notice, I put here that all these advances, I put here this lambda equal to 0, okay? And it's because all the theory of gravitational waves in full general relativity was done for the case with vanishing cosmological constant. So there's another observational fact, which is that the cosmological constant is positive. And somehow now we have this paradox. So I want to convince you that it's necessary to address the problem of gravitational radiation in full GR with a positive cosmological constant. Okay, so some open questions are like, for instance, how to tell when gravitational waves arrive at infinity. So, and this is the most basic question that we have to ask. So how would one aim at finding some kind of gravitational energy momentum or charge associated to gravitational radiation with a positive cosmological constant if one doesn't know how to tell when gravitational waves are present or not? So this is the first question that one has to answer. Then can one find an asymptotic group of symmetries? I will give you more details on all these topics later. So is there a way of imposing a no incoming radiation condition? Which is the energy carried by these gravitational waves? Okay, so we try to give an answer to the first three. The fourth point is still open, an open question, and has to be addressed. And this is just a list of works by other people that appeared in the last years in the literature. And so I just wanted to say here something, and it's that some of the works use techniques that were well known when the cosmological constant vanishes, and the problem is that if one wants to adapt all these techniques, all these methods that were known in the case with vanishing cosmological constant, they simply do not fit very well with a positive cosmological constant. And there are geometric and topological features of this cosmological setting that justify what I'm saying, and I will show you them. So okay, so what we did was a study of the asymptotic structure. So we studied infinity from a covariant and gauge-invariant point of view, and with this study we characterized gravitational radiation. Okay, so this is what I'm going to talk about. It's based on a series of papers. Of course, I'm not telling all the things that are in these papers, but so the first two more or less contain the most fundamental ideas of our works, and the last two are quite long and have the developments, of course, of the results, and also the results. And there is some related work about the Pilling theorem that we have done for an arbitrary cosmological constant. And if time allows, I will say a couple of words about it. Okay, so I'm going to be heuristic now. Yes, this is just to give you this big picture of things, right? So I'm going to set the cosmological constant to 0 now, and I will work in a conformal completion. This means that infinity is represented by a hypersurface, and when which is this line that I'm drawing here. So time goes upwards and light cones are at 45 degrees. So this is a lightless hypersurface. It's typically denoted by this letter, which is Scri. And so I will mention Scri, infinity, and conformal boundary in the talk, and they mean the same, okay? They mean infinity. So the problem is to study gravitational waves that arrive at infinity, that arrive at this hypersurface, okay? So what it is known since the 60s and 70s is that there is some gauge-invariant tensor field, which is this N, typically called News tensor, which has the interesting property of vanishing if and only if there's no gravitational waves at infinity. And based on this object, one can construct an energy momentum, and one can write a massless formula that tells you how much energy is carried away by gravitational waves. Okay. In addition to this, one can study the asymptotic group of symmetries, which is the so-called Diana's group. And one can do other things like implementing symplectic methods. This was done in the 80s by Ashtekar and Strebel. Okay, so all this is known and applies in the case of a vanishing cosmological constant. What we did was first study this case, but instead of using the new tensor, we use a different object, which is this vector field P that I will define later. Okay, this vector field has a very strange name. I don't like it. It's this asymptotic square momentum, but there is nothing funny about it, okay? Yes. And the good thing of this alternative characterization is that it's geometric, and you can use it in the case with a positive cosmological constant. And that's what we did. So if we go now to the case of a positive cosmological constant, now infinity is no longer a light-like hypersurface. Instead, it's a space-like. So the causal character changes, and this changes everything. So that's why all techniques do not apply very well to this scenario. Okay. Yeah. Comes from superenergies. Yeah, exactly. I will talk about the Bel-Robinson tensor in a while. So again, we consider some gravitational waves. Okay. And now we have a condition that tells you when gravitational radiation arrives at this price, arrives at infinity. And indeed, we did a further characterization. So we found a first component of news. There's a second one. And also we studied the asymptotic symmetries and concept charts. Okay, these are things that one can explore with this new characterization. So yeah, that was it in a nutshell. So and now the talk, it's going to be maybe more technical. I don't know. Maybe for some of you it's more technical. Maybe for others of you this is going to be boring. I hope no. So why we use conformal completions at Penrose? Well, because I have said they describe infinity as a hypersurface, and this has a lot of advantages. And why are we interested in infinity? Well, because physically speaking, this corresponds to the radiation zone. So it's where gravitational radiation emerges neatly. Okay, that's why we work at infinity. So a conformal completion is the following. So I have an embedding of some physical spacetime. I'm using hats for the physical spacetime, okay? So I'm on physical or conformal spacetime M, such that the interior corresponds to the physical spacetime, and the boundary represents infinity, which is this described. So the matrix, I have G and G hat. G is the conformal metric. It's related to the physical metric by this omega, which is the conformal factor. By the way, I'm using alpha. So Greek indices denote abstract indices in the spacetime, okay? 4-dimensional spacetime. I work in 4 dimensions. And this omega is positive in the interior and vanishes at the conformal boundary. And I can define the normal as the gradient of omega, is this end, right? Do we have something to show over here? Can I use this? Yeah. Yeah, you can. Okay. Very well. And also, we will assume that G hat, the physical metric, is a solution to the instant field equations, and we will consider only these two cases. So vanishing cosmological constant and positive cosmological constant. And the energy momentum T hat vanishes at the sky, so that this thing here is smoother. Okay. Now, in general, the sky has two disconnected components, which are typically called sky plus sky minus. This is future infinity and past infinity, but everything that I'm going to tell you applies equally to both of them. So I won't bother in putting plus or minus. I will just write sky instead. So sky is like when the cosmological constant vanishes, it's a space-like when this cosmological constant is positive, or it's time-like when this is negative. Okay. Very well. Now there's an important thing here, and it's that when you work with conformal completions, you have this conformal gauge freedom, and I will call this just gauge freedom from now on. So this gauge freedoms means that you can rescale the conformal factor by some little omega, which is a positive function. So if you want to have a physical, if you want to make a physical statement, of course, this cannot be gauge dependent. And what happens if you fix completely the gauge is that you don't have any freedom to check whether your equations are gauge invariant or not, right? So instead, we partially fix it. This is a common choice in the literature. And so you can choose omega such that the normal to scribe has vanishing covariant derivative at the scribe. So nabla is the Levi-Civita connection of the spacetime. But still there is a huge residual gauge freedom. Okay, so you can still make gauge changes using omegas that fulfill this equation. Very well. Now another fact is that the Weil tensor vanishes at scribe. This is independent of the choice of cosmological constant. And because of this, one works with a rescaled Weil tensor, okay, which is regular at the scribe and in general is non-bunch, which is this little bit. And now I'm going to list just some space-time tensor fields that that we use. So one is the Schouten tensor, which is this combination of the Ricci curvature and the scalar curvature of a space-time. Then we have this Friedrich scalar, which sometimes I think more often is called S, not F, right? And then there is this rescaled Cotton tensor. This guy tells you about the content of matter of the space-time once you use the Einstein field equations. And so here is the rescaled Weil tensor that I just introduced, and then we have this rescaled energy momentum, okay? And all these fields enter these conformal field equations, which I'm trying to evaluate it as scribe, okay? And so here you see how the cosmological constant affects the causal character of the conformal boundary, because this was the normal to the boundary. And I'm putting this in red because I'm going to use it later on a couple of times. And now we find some new object, which is the rescale or new in this context, which is the rescale version of the Bel-Robinson tensor. So essentially, it's this D, which has this, is computed in terms of the rescale Weil tensor. Here the star is just the standard Hodge dual operation. And the standard Bel-Robinson tensor has this very same definition, but using the Weil tensor. The thing is, this is what I'm calling T, the standard Bel-Robinson tensor. The thing is that because the Weil tensor vanishes at the scribe, of course, it's a zero at the scribe. So I have to use the rescale, okay? And this is regular at the scribe. And now I'm going to make a disclaimer and some clarification. So all the quantities related to the Bel-Robinson tensor are typically called superenergy tensor, superenergy quantities, scalars. So this is a very bad name. It doesn't mean it's not related with supertranslation, it's not related with supersymmetry or whatever. But for historical reasons, it's there. So the thing is that people think that they are going to do obscure things with energy using this subject. The thing is that this subject has not units of energy. That's why it has this strange name of super energy thing. But we are not using it for defining any energy. We're using it because it shares a lot of algebraic properties with energy momentum of the electromagnetic field. And you can use these properties are very convenient to characterize gravity. Okay, this was this. Yeah.
So let me just see. So D go as an omega minus one, right? So the small D. So the big one has omega minus two, right?
Yeah, exactly.
But omega is
yeah, that's right. But this guy here is regular style.
Right.
Yeah. So if you put here the Weil tensor, it's zero like omega squared, right? So if you divide twice by omega, this is what it is. The thing is that little d is regular. So. And okay, so we use this object to define the P that I was showing you in the introduction. And we use here, you see this N, which is the normal to scribe. So we complete this super momentum using the rescaled Bel-Robinson tensor and the normal to scribe. Very well. And now I'm going to tell you about the case with vanishing cosmological constant. So again, scribe is like that. So infinity is like that. And the distinguishing feature of this case is that the normal to scribe, as seen as a vector, is tangent to scribe. And this gives you a natural way of evolving fields within scribe. And this is completely different in a case with a positive cosmological constant, as you will see. Okay. So I will introduce arbitrary basis of vector fields tangent to scribe and a dual basis as well. So I'm using little a, little Latin indices, sorry, for describing quantities tangent to scribe. So I have this first fundamental form, which is degenerate with n being the generation vector. And also the second fundamental form vanishes because our partial gauge fixing. Okay. One can introduce an inverse, which is not unique due to the generation of the metric, and also a volume form. So this epsilon is the volume form in the scribe, this zeta is the volume form of the spacetime. Now, I will define a cut as some any closed space-like surface, which is transversal to the generators everywhere. So I will assume S2 topology in this case, but you can relax this thing depending on what you want to do. And also, E and W are bases on this cut. So I'm using capital indices to denote indices that are two-dimensional. Okay. And I will define this vector field as that one that fulfills these conditions, which is put it in. If you put it in words, this means that L is the unique light vector field, which is orthogonal to the cuts, but it's not aligned with N. So here we have two cuts, S1 and S2. So indeed, you can consider a collection of cuts. And then if they're not intersecting, you have a foliation. And now we do the pullback of the Schouten tensor that I showed to you some minutes ago. And we define this S bar here. And also we define the following components of the rescaled tensor. So this D and this C do not contain the whole information of the rescaled tensor because N is like that. So they are not the standard electric and magnetic parts of the rescaled tensor. And we can relate these two guys using that equation there. So this is the relation between them. And indeed, we can go further and make the new tensor appear here, as you will see. But for that, one has to use the following result. So there is a unique symmetric tensor field rho on scribe, which is orthogonal to N, who has this strange conformal gauge behavior, okay, and satisfies this equation in unique conformal frame. Also, this has a fixed trace and has this form if you choose a conformal gauge such that the cuts have are round spheres. The metric of the cuts is the round metric. And this tensor was originally found by Gerg in the 70s, and it plays two important roles. The first one is to define the new tensor. So indeed, what rho does is to subtract from this S bar the gauge, the band gauge behavior, making this N a symmetric traceless gauge-invariant orthogonal to N. And this is a new tensor. Okay, this can be justified to be the new tensor. And I have some backup slides that I could show you later. But okay, anyway, so with rho I define the new tensor, and due to the properties of rho, I have this connection between the new tensor and the rescaled tensor. Okay, And this field in general has non-vanishing Lie derivative along n, which means that has some evolution within Scri. Another feature of this case, when the cosmological constant vanishes, is that one can consider some universal structure common to this kind of spacetimes, which is this conformal family of pairs, where you have the degenerate metric and the degeneration vector. And if you define the transformations that preserve this structure, then you get the PM's group. So there are a lot of ways of defining the PM's group, but this is my favorite one because you don't have to use coordinates or anything that is not covariant, right? So the infinitesimal generators fulfill these, the generators of infinitesimal symmetry, fulfill these equations. And within this group, there is a subgroup of super translations, which are those that are proportional to n and fulfill, and this function alpha fulfills this relation. Very well. The second role that this tensor rho plays, and it's because I want to convince you that this rho tensor is very important. So the second role is that you can define a subgroup within these super translations of translations. And are those super translations whose alpha, remember alpha is the function appearing there, so whose alpha satisfies this equation. You see that rho appears here. I will come back to this equation later. Okay. So now we use, yes. It's not a lapse. I mean, maybe you can think of it as a lapse.
Because n was the one time.
Yeah, maybe. Yeah, you can think of it as a lapse. Maybe I don't know. I don't think of it as this, but maybe yeah. Mm-hmm. Yeah. So now we define this this asymptotic supermomentum, this P. Okay, this is the definition, and after some calculations, you arrive at this this set of equations that relate P with the new tensor. So we proved the following theorem, which essentially says that there is no gravitational radiation if and only if this P vanishes. And this has a more geometrical statement. So what you can say is that this is equivalent to P being orthogonal to all surfaces within delta, where delta is just an open portion of Scri or Scri, okay, as you want, and not collinear with n, or that n is the principal null vector of the rescaled by tensor. And you will see the correspondence in the case with a positive cosmological constant. So now, what happens with a positive cosmological constant? That the Scri is a spaceline. So I'm drawing here a plane because actually you can think of it as a plane if you want. But this is just to remark this difference. So now the normal, of course, points outwards because it's time-like. So you no longer have like an intrinsic evolution direction. And so there is a whole structure missing now. And yeah, you can draw it as a plane if you want, because okay, you can think of it as a 3-sphere, okay, and then do the projection to the plane. But of course, Scri can have different topologies. So, but you can always think of it as a 3-sphere and then remove a set of points, right? If it has R3 topology, then you remove a point. If it is a cylinder, then you remove 2 points, and you can remove any number of points that you want in principle, right? And so now n is time-like. So you can normalize it. And just for convenience, I will use sometimes this little n, which is unique, okay? The second fundamental form vanishes again due to the gauge choice. And now we have this D and this C. So, but they are different. This D and C are different from the previous one. So now they do determine all the information that is in the Bel tensor. rescaled by tensor, sorry, because they are the standard electric and magnetic parts of the rescaled by tensor. And we have the intrinsic Schouten tensor of scribe. So H is the metric on scribe, and this is just the curvature on scribe. Okay. Very well. Using again this equation, we have this relation. So now you see that things are different. So C, the magnetic part, is completely intrinsic. So it depends only on the geometry, in the sense that all quantities appearing here are geometric quantities of the scribe. We have the curvature, which is this Schouten tensor. We have the relativity Lambda part of scribe, and we have the volume form of scribe. But D, the electric part, is no longer intrinsic, because here we have the space-time Schouten tensor and the covariant derivative of the space-time. And indeed, you see that there are some derivatives that go outward of the scribe, right? So, so this is no longer intrinsic. And now again, we take our asymptotic supermomentum. Since now I can normalize N, sometimes I will use this capital P. It's the same as P, only that we use the normalized vector field length just for convenience. And I can distinguish two parts. So the first part that is tangent to the normal is this quantity W that is positive. This is called super energy density. And then I have a tangent part, which is called superpointing vector field, or asymptotic superpointing. Why asymptotic? Well, we are infinity. Why super? Well, because it's related to the Bel-Robinson tensor. Why pointing? Because it plays a similar role as the pointing vector in electromagnetism. So the pointing vector in electromagnetism gives you the flow of radiation to a given observer. And somehow this thing does the same, but with gravitational radiation. The thing is that, well, you can say, okay, but this pointing thing is observer dependent. Well, yes, if you pick an arbitrary observer, but the thing is that now the observer is determined by the geometry, by the conformal geometry. It's N, it's a normal to scribe. There's no choice, okay? So there is no ambiguity here. Now, if we want some radiation condition, we expect some features. The first is that it has to be gauge-invariant, as I was stressing at the beginning. It has to be observer independent, and it has to be strictly asymptotic. So, so now P fulfills all these things, right? But there is more. And so it's that the necessary and sufficient information has to be encoded in this triplet, where here I have a scribe, and it's metric, or the conformal class of metrics, and D, where D is a TT tensor. I mean that it's traceless and divergence free in vacuum. And there is a result at Friedrich that says that the solution to the Lambda vacuum Einstein field equations is determined by this initial data set. Okay, so Friedrich is telling us all the information that you need has to be encoded here. So this is a message that I want to transmit for those of you interested in gravitational radiation, is that if the cosmological constant is positive, it's not enough with the intrinsic geometry of a scribe, you need D as well, okay? So this is a condition. So there is no gravitational radiation on a scribe or on a subset of a scribe if only this asymptotic superpointing field vanishes. But now you can restate this in a more geometrical way. So this is equivalent as saying that P is orthogonal to all surfaces within delta, or as saying that N, which is time-like, remember, is a principal vector in the sense of Pirani. This, in the sense of Pirani, means that it lies in the intersection of two principal planes. And you see the correspondence with the geometric description of the absence of gravitational radiation when the cosmological constant vanishes. So now let me give a closer look to this initial value problem. So, okay, very well. You have this radiation condition it tells you that there are no gravitational waves if this P vanishes. And then we have this initial data by field. Okay, now let me remark that this asymptotic tensor is not the second fundamental form of criterion or anything like that. It's just a asymptotic tensor. And then from the first pair in this data set, I can compute this Cotton-York tensor because I have here the curvature, I have here the intrinsic Levitch interconnection, I have the volume form. So it turns out that you can write the gravitational radiation condition as this commutator. So there are no gravitational waves if and only if the commutator of T and Y vanishes. So you see here the interplay between both sectors in the initial data set. Are there any questions?
Does this condition relates to the fact that H is conformally flat or not? Because I remember
Yes.
with Ashtekar he mentioned something like that.
Yes, the thing is, so SCRI is conformally flat if and only this thing vanishes.
Oh, okay.
So this is just a particular case in which there is no gravitational radiation. Because if Y vanishes, then
Okay.
Okay. But in general, you can have situation where SCRI is not conformally flat and there is no radiation.
Oh, okay.
Okay. And if you look to this from the perspective of the space-time, actually D, as you notice that I was using the same letter, coincides with the electric part of the rescaled by tensor, and C, the magnetic part, coincides with Y. And these fields have this form in terms of this sigma, where sigma is the shear of N. So you actually, if you want to write things in terms of shears, then you have to use this equation. And now, for those of you who are fond of the Newman-Penrose formalism and spin coefficient formalism, if I pick a couple of null directions that are coplanar with N, okay, this K plus and K minus, for instance, then I can write the condition in terms of Weyl scalars. So these two equations in terms of Weyl scalars gives you the presence of gravitational. This is just another way of writing. And then one can go further. How much time do I have?
15 minutes.
15
Oh, well,
minutes? Okay.
10 minutes.
10 minutes?
for
Okay.
questions.
Okay, thank you. So one can ask more questions, like, is there a new tensor, like the one that I knew from the case with a vanishing cosmological constant? So we explored this question and developed a general framework to find new tensors. And I'm not going to explain the method, but only to give you a result that is important, which is the existence of this generalization of the raw tensor that I was showing to you. So now this is for any two-dimensional Riemannian manifold. Here you see that we have S2 topology, but I will say something about this in a moment. So essentially it's the same raw tensor that I was describing before, but it's general. It's not for a particular setup of SCRI with vanishing cosmological constant, right? And indeed, we generalize it for other topologies. So for instance, the cylinder and the plane are included. Right? So now what I'm telling you is that we have a raw tensor when the cosmological constant is positive too. And this piece of information can be used to show the existence of a new tensor that we call V, okay? But it's not the whole new tensor. It's just one piece. So why? Because this V is determined by the geometry of SCRI. And as I was saying, that's not enough to describe gravitational radiation. So there's a second component that has to come from the electric part of the Weyl tensor, from V. And now, so if you remember, at SCRI, when the cosmological constant vanishes, there is this nice universal structure. So you have the generators of SCRI that gives you like a privileged direction, and then using this universal structure, you define the symmetries, right? Now we don't have anything like that because the normal is no longer intrinsic. So if one wants to define something like asymptotic symmetries that look like the Bian's group or wants to promote things that live on cuts to fields that live on scribe, then one needs more structure. And this structure is a congruence of cubes. Okay, so we studied what happens if you consider an arbitrary congruence of cubes. And so we have a scribe. Okay, on top of it, we consider some cubes. And then we define this quotient, this x, that is a two-dimensional manifold. And on this S, I'm going to introduce, which is just the projected surface, okay, with respect to the congruence with respect to M. I define a couple of bases as before, as I was doing for the cuts. And also, I have this projector. I have that I can take pullback of fields on scribe to S. And in general, all the quantities that I define on this two-dimensional manifold depend on V. V is the parameter along the cube. And that's why I'm using underparts to denote that the quantity that has an underpart is two-dimensional, but it depends on V. So actually, one has a family of connections, one has a family of covariant derivatives, and one has a family of metrics. Okay, so with this machinery, we can do things like this. For instance, we consider that the scribe is equipped. This is something like the universal structure, but it's not universal, but it's something that you can consider, okay, when it's endowed with a foliation. And then you consider the conformal family of pairs consisting of the projector and the vector field that gives you the congruence. There is a particular case which is very fruitful, and it's when this congruence actually defines a foliation by umbilical cuts. Umbilical means that the shear of M vanishes. Okay? So if we assume that the scribe is endowed with a foliation, that this congruence is actually a foliation, then we can generalize the raw tensor that is defined on a cut to a tensor field that lives on scribe. And also, we can explore the existence of symmetries as those that preserve this equipment. And that's what we did. We call it equivalent symmetries. So essentially are the symmetries that transform a conformal pair to this thing. These actually are the conformal transformations because they don't act with the same factor in P and M, but with different factors in general. It can be the same. Okay. And also we derive these symmetries from the space-time. And the most interesting case is when a scribe is foliated by umbilical cuts. And then you can show that there is a subgroup that we call retranslations that are symmetries that are proportional to M. So you see here that, well, this looks similar to the BM's group. It's not the BM's group, okay? And by the way, this is infinite dimensional subgroup. And also now we take rho, which plays this second role, right? And we can identify a set of translations. So we define infinitesimal translations with a positive cosmological constant as those retranslations whose alpha fulfills that equation. And I think I don't have time to show you the balance law, so I will go to the conclusions. So the thing is that this new characterization, we say that it's naturally adapted to the tidal nature of gravity because it's based on the Weyl tensor. And also it gives a direct connection between the existence of gravitational radiation and the algebraic properties of the rescaled Weyl tensor. It has a neat correspondence between both scenarios, and it does not depend on any particular gauge or any choice of coordinates. And in particular, when the cosmological constant is positive, so we saw that it's an interplay of the initial data according to Friedrich, and we can find new tensors, and also we can promote them with some additional, adding some additional structure, which is a congruence of curves, to tensor fields on the three-dimensional manifold, and identify a subgroup of translations. So I haven't talked about conserved quantities, there was no time. And the final remark is that we applied this to several examples, and it works. Okay, so that's all. Thank you for your attention. Sorry for this inconvenience with the laptop. And yeah, thank you.
So we have time for questions. So any question for Fran?
I have probably a very simple question. What is there something particularly difficult about the negative cosmological constant case? Why is that completely excluded?
Well, it was excluded at the beginning because we inhabit a universe with a positive cosmological constant, right?
Okay.
But of course, technically, the weird thing is that so what would be maybe more difficult to begin with is that this object that we use, which is the supermomentum, is defined with respect to causal vector fields. So time-like in the case of a positive cosmological constant, or light-like in the case of a vanishing cosmological constant. And now with a negative cosmological constant, this normal to describe is space-like. So I don't know. We haven't explored that case, but I think that that's the main difference, that one has to look into it carefully. Thank you. Thanks.
Any other question?
Towards the beginning, you mentioned this symplectic method against line 11. I didn't know anything. I was curious to know a bit more of what that means, and also maybe how that compares to the thing.
Yeah. So I haven't worked with symplectic methods, but this is something that Ashtekar implemented because he was looking for a quantum, an asymptotic quantization of the gravitational field. So he tried to understand the dynamics of the degrees of freedom of gravitational radiation at infinity from the point of view of a symplectic form, which essentially one takes as the fundamental variable a connection. So first one has to define a space of connections, and in this space of connections that represents the degrees of freedom of gravitational radiation, this is a long story, but one defines a quantity, a symplectic form, that gives you the evolution within this space. So that somehow this is telling you the dynamics of the gravitational field. And that's what I meant by symplectic methods. And actually, you don't have to do anything quantum. If you do it, you can recover the standard energy momentum formula for the gravitational field in asymptotically flat spacetimes. And it's an interesting thing to explore. Indeed, I'm working something towards that thing, but yeah.
Any other question?
Tell me if I'm so the study of gravitational symplectic behavior background is of interest in itself, of course, but to practical application, seems that it's of interest for sources that are at almost cosmological focus. Otherwise, we can consider our space-time and symplectic. Is it correct or not?
Well, this is a topic of debate. It's true that probably this problem is more important conceptually to understand the actual laws that prove gravitational radiation. But also, I'm not, of course, I'm not an experimentalist. I'm not but the thing is that you could consider other sources of gravitational waves, such as gravitational wave background, right? And I think that for that case, this would be interesting. Also, there have been approaches to understand gravitational waves in the presence of a positive cosmological constant at the cosmological horizon. Instead of using scribe, one uses the cosmological horizon. But I have a problem with that, and it's that it's not true. It's not truly an asymptotic observer. So the things at the cosmological horizon are not like the things that are at the sky when the cosmological constant vanishes, although there are similarities due to this causal character. There's something else. So you're doing something else. So it depends. I think it's a matter of deciding how do we want to understand gravitational waves? Do we want to just keep what we know from infinity of the setup with a vanishing cosmological constant, and there we go? Or do we want actually to go to the detail and see how a gravitational, a cosmological constant affects the dynamics of gravitational waves towards infinity, which is a true asymptotic observer?
No, that I understand. Source that one here, five years from here, it seems to be that you can get now, if it's at 10 billion light years, then
Exactly. Indeed, what would be nice was to have these methods too and see which one works better. I'm not, I mean, and yeah, I think that balance law, for instance, that you can build with these methods, it would be nice to test this balance law as diagnostic tools somehow for waveforms. But of course, this is something that is yet to be explored. But yeah, there's a debate about this. Thank you for the
Other question?
Do you really use the Einstein equations? So it's a geometric construction. Yeah, so actually, it's the condition is symmetric, right? But I guess that when we use the Einstein field equation, is for the balance law that I was not showing. But so essentially, but I can show it briefly, right? So essentially, we use the divergence of this supermomentum to build some balance law. And to make some sense of this, if you don't have, this is the energy momentum tensor, well, a piece of it that survives at infinity, yeah? If you don't have this, here you have a geometric form. But if you want to make sense of this at infinity, like balance law that has some matter contribution, some gravitational wave contribution, then we use explicitly Einstein. But otherwise, the conditions are geometric. Could you do similar construction courses depending on the conformal picture? Yeah. Could you do a similar construction some finite border like the matching surface in the star? Some world tube or something. Sorry? I was in a world tube. Yeah. Well, I would say that this thing actually, it's more in the spirit of our previous comment, right? So it's more in the spirit of why don't we use the cosmological horizon and then do some matching with, I don't know, with upper boundaries. You can use it. You can apply these things, but to disentangle from everything the radiative degrees of freedom would be much harder, because as I was saying, gravitational radiation emerges naturally when you go to infinity. If you don't go to infinity, the equations are much more involved. But you can do it. Actually, another thing which I'm working on is to try to apply this to horizons. Not necessarily cosmological horizon, but yeah. But I don't know. It's something, of course, that could be explored.
Any other question? If not, I have. Oh, there's one. Yeah, I didn't see you.
Like physical space.
Okay.
Your solution PR.
Okay.
And you know the spatial metric and temperature.
Okay.
Then you can build the electric part just from those and stuff.
Okay.
Yeah, that's not true. Right, because you said that the D is independent of the
Yeah,
in square.
that's true.
So what goes wrong? Like, why doesn't that result carry over?
Well, I don't know if it carries over when you go inside the space.
Yeah, I guess if you sort of tail it down, would that result?
Of course, I
I'm
guess.
asking, like, why do they become independent quantity at square? You have any sense of that?
Not I don't, sorry. I mean, it's clear that there are different things. That's for sure. You have the geometry of the square, and then you have this extra piece of information.
Yeah.
Maybe if you,
it's funny, right?
it's funny.
They're no longer.
Yeah, that's funny. I don't know. Maybe Edgar, you.
Yeah, actually, I was thinking. So what happens is that when you take the constraints of the conformal line simple equations and you evaluate that scry, you can solve explicitly for the what would be the second fundamental form, and is not electric, and you can solve that directly in terms of the H's and everything, in terms of the Schütten tensor, I think.
Exactly. There's exactly this.
And becomes gauge, actually appears a gauge quantity times derivatives of Schütten. So actually you can even make that thing zero at scry. So scry is sort of gauge.
And this D, if you see it from the perspective of these Beckerman-Graham expansions, so I think so in this series of expansions that you get towards infinity, right? You have like the first term or the zero term is like the metric of scrap or the would-be scrap. Then you have, I think, one or two terms, I can't remember, that are essentially curvature terms that depend on this metric. And then you have a new term, and that's D. But it's separated. It does not depend anymore on the first term. And so, I mean, the same thing that you can see from the conformal simple equations, you can see it also in this expansion. It's I don't know, it's interesting. It's an interesting question. Thank you.
I'll make a really fast question, if I may. So, what is the connection between this work and the work of Carlos Peón Nieto, where he establishes this connection between symmetries at scry? Can you determine or construct the tensor, the vector P, in terms of the killing vector or conformal killing vectors at scry that Carlos Peón develops?
The construction of so the characterization of the radiation that we did is independently of the existence of any symmetry.
Okay.
You don't need, I mean, if you have it, okay,
yeah.
Use it if you want, but
there's no any connection saying that if you have the symmetry, that then sort of boils down to being certain type of space, and then it means that automatically something would be zero, that your P would be zero. Something like saying if there's a symmetry, then therefore P has to be zero. So
well, yes. For instance, well, I don't know exactly at once, but for instance, in the case of Petrov-type D, there might be a case in Petrov-type D in which you have radiation, and another case in which you don't. Okay, and in the cases in which you don't, actually you can D and C, the cotton-York tensor and this TT tensor, are proportional. And you can write them in terms of this conformal killing vector field. that is inherited from
Yeah.
the space. And this theorem tells
Yeah.
you that if you have a
Yeah.
conformal
Yeah.
vector space. So, okay, in that sense, look,
Mhm.
there's a relation, right? But I don't know if it's just like
A coincidence.
coincidence of the
Uh,
construction
yeah.
more than
Mhm.
something more fundamental. But yeah,
Yeah.
that's interesting. Yeah.
Well, if there are no more questions, let's thank the speaker again.
Thank you.
If you enjoyed the video, like and subscribe.